Hey Todd, this is John. So this is my demo. Thank you for listening. I'm using Explain Everything to show you exactly what's going to happen. So I'm going to walk in, introduce myself, and then I'm going to say that I'm there to talk about multiplication. And my idea is that I want to build a swimming pool. And so to build a swimming pool, I have to buy the land, and the land costs money, and they charge us by the foot. So to figure out how much money it's going to cost, I have to figure out how big my pool is. So my first design is this one. My pool is only 1 foot wide, but it's 10 feet long. How big is my pool? Well, the kids are going to talk. They might count it up, they might skip count, or they might just know that 10 times 1 is 1. And hopefully they'll say, well, I know that 10 times 1 is 10, so it's 10 feet wide. Okay, so next I'm going to say, well, what are one of the problems with my first design is that it's just too small. It's only 1 foot wide. I couldn't even swim in it. I couldn't even fit in it. So I need to make my pool a little bit bigger. So what I've done is I've taken another row that's identical to the row that we just figured out, and I added it to my shape. So how big is this pool? Well, we know that it's 10 feet wide, and now we know that it's 2 feet wide, and it's 10 feet long. Well, the kids might, hopefully they'll be doubling their 10, and they'll say, well, if the first one is 10 and the second one's 10, then 10 plus 10 is 20. Some might say, well, I skip counted by twos, and I went 4, 6, 8, 2, 4, 6, 8, 10, and then I doubled the 10, blah, blah, blah. But the goal is that they're arriving at 2 times 10 equals 20. So the next thing I'll say is that in a real life design, it probably wouldn't show the grid of how many feet are in it, just like in a real life pool. There aren't squares that mark off every foot. So this pool is 10 foot long and it's 2 feet wide, just like the shape that we looked at before. How big is this pool? So some kids, hopefully all the kids will say, well, it's still 20 feet wide because the shape is the same even though I can't see the squares. And then I might say, well, what if I'm not comfortable with 10 times 2, or I'm not comfortable with that shape and I still want to have those two 10s? Can I just draw a line and make this into 110 and 110? I'm going to break that 2 into 1 and 1. And I've got 10 times 1 and 10 times 1. I've got two 10s. I can add them together to make a 20. And the kids might say, oh yeah, it works the same way. So next I might say, what if there's a person who's not that comfortable with their 10s facts, but they're really comfortable with their 5s facts? And they would rather break this 10 into a 5 and a 5. So we'll split that in half. Now we've got 5 times 2 and 5 times 2. 10 and 10. And we know that 10 plus 10 makes 20. The answer is the same both ways. Both strategies work. So next I'm going to explain that when we use a rectangular shape like this to figure out a multiplication problem or to figure out how big something is, this is called an area model. And an area model really helps us whenever problems or shapes get so big that they're bigger than multiplication problems that we might know from our times table. And this one is going to be bigger than something that they might have learned in the times table. This shape, this swimming pool, is going to be 6 feet wide, and it's going to be 14 feet long. So my question is, how big is this pool? I'm going to let the kids think about it for a second, and then I'm going to say, well, I'm going to give you a strategy that I like to use. I want to break that 14 into, I want to take the 4 off the top right away. And then, I'm a person who's not as comfortable with my 10s facts as I am with my 5s facts, just like I just talked about. So I'm going to make the leftover 10 out of the 14 into a 5 and a 5. Now I've got these three problems. 6 times 5, because the 6 and 5. 6 times 5 again, and 6 times 4. 6 times 5 is 30, 30, and 24. Now all I have to do is add up what I've got. I've got a 30 and a 30, making a 60, plus 24 is going to equal 84. So next I'm going to ask the kids and say, is there another way to break up this shape to help you solve the problem? And is there a way that you think might be easier than the strategy that I used? Hopefully, kids will be jumping out of their seats to say, well, I think it's easy to break that 14 into a 10 and a 4. And then I can do a 10 times 6, which is 60, and 6 times 4, which is 24. 60 plus 24 is going to equal 84. And then I'm going to ask the kids again, is there another way to solve this problem? They might come up with, let's say one kid is like, I'm really into my 12s, and I know 12s inside and out. And so 14 is a 12 and a 2, so I'm going to break that into that. And I'm much more comfortable with 12 times 5 than 12 times 6, so I might break that 6 into a 5 and a 1. Now I've got 4 problems inside of this. I've got 12 times 5, 12 times 1, 5 times 2, and 2 times 1. I know 12 times 5 is 60, 5 times 2 is 10, 12 times 1 is 12, and 2 times 1 is 2. So I've just got to add those up. I'm going to start with the 60 and the 10 to get to 70. Then I'm going to add a 12 to get me to 82. And finally, I'll add that 2 to that 82 to get me to 84. That 12 strategy might be the one that I volunteer because I know that it's much more challenging to think about cutting it apart both horizontally and vertically. Okay, so our conversation is done. Now the kids are going to go off to work. They're going to be split into groups of 3. The goal is that 3 kids are talking, figuring out 3 different strategies together, and then showing in 3 different ways. So there's a lot of communication that has to happen, and then there's a lot of difference in thinking. And one of the problems they'll have is 24 times 8. My hope is that there's a quick kid who says, I know 20 times 8 and 8 times 4. But then there's another kid who's like, well, it's so much easier to break that into a 10, and a 4. And then there might even be another kid who says, well, I'm more comfortable with that 8 as 4 and 4. I'm not really that sound with my 8's facts. So I got 40, 40, 40, 40, 16, and 16. Right? This is 20 and 4. It's 160 and 32. And then another kid is probably going to come up with like this, where there's say, well, I've got 12 and 12 because I'm really good at my 12s. And then I've got 12 times 8, which is, 96 plus 96. And then, is that right? Yeah. And this is much more tricky to put together than this or this, which is what I want. At the end, I want the kids to be able to say, well, this is the most efficient way, and this is a way that seemed like it would be easy, but it ended up being really hard. The kids are going to work. I'll have a bonus, or I'll have a variety of problems for them to solve if they do it too quickly. And then I'll also be able to let them figure out how much it's going to cost. So I might say that it's $3 a square foot. So if their pool is 96 square feet and it's $3 a foot, how big is it? And you have to use an area model to solve it. So then they're here, they've got 396, and I don't know how they might do that, but there might be a kid who just says, I know 90 and I know 6. 90 times 3, I know 9 times 3 is 27, so 90 times 3 is 270, 6 times 3 is 18. That is $288. Something like that. Let me know what you think. I'm still playing with the problems because I don't know if they're too easy or too hard. This is actually the third time that I've made this presentation, and I've changed the problems 3 times. So let me know, and I'll also include some other stuff via email. Thanks for your help.